Hello everyone, this video is going to help you prepare for our biochemistry test, which is our test 2. The first question on your review sheet is, what three subatomic particles make up atoms? In this picture you can see that there are three different particles, subatomic particles. One is proton, one is electron, and one is neutron. You can remember the name and the charge of each one of the subatomic particle by looking at the name itself. So the first one is proton. Pro is something good, something positive. So each proton is plus one charge. So when I ask you what is the charge of a proton, don't just write plus, write plus one instead, so that you can use that for calculations of other kinds. Neutron, because it has the new part, it's neutral. So it has no positive or negative charge. And then we have electrons that are negative one charge. Make sure you write negative one. So the next question is, you need to be able to identify the number of protons, get rid of this, the number of protons, neutrons, and electrons by looking at the periodic table. We had that on our quiz last week. If you didn't do too well, I'm going to make another video going over the questions on the quiz. So make sure you watch that other video and so that you're as ready, as prepared as possible for Monday. In order to identify the number of protons, neutrons, and electrons by looking at the periodic table, you have to know these two very, very important equations. So for every one of these boxes that you see on a periodic table, the upper left corner has a number. That is your atomic number. Make sure you don't get confused between the atomic number and the atomic mass. So the atomic number equals to the number of protons, which also equals to the number of electrons. I want you to assume every time, unless I tell you that a certain atom has a positive or a negative charge, I want you to assume that this atom is neutral, right? In order for something to be neutral, you have to have the same number of positive charges and the same number of negative charges, meaning that you have to have the same number of protons and the same number of electrons. So take nitrogen as an example. The nitrogen proton number, or the atomic number, is 7, so the proton number will be 7. What about the electron number? All right, if we have 7 protons, right, that gives you a plus 7 charge. In order to get to neutral, which is 0, we need a negative 7, and that negative 7 comes from the 7 negative 1 charged electrons. So we have 7 electrons. So just write this down real quick. For nitrogen, the proton number is 7, and the neutron number, and the electron number is also 7. And then, if you want to find out what the number of neutron is supposed to be, you use the atomic mass equals the number of protons plus the number of neutrons equation. So, or you can also write it as number of neutrons equals to atomic mass minus number of protons. When we are looking at the atomic mass of an atom, we only take the number of protons and neutrons into consideration because those are the subatomic particles that weigh more and is more significant than the weight of the electrons. So if we were to find the number of neutrons of nitrogen, you would take this number, which is the atomic mass. So for nitrogen, the number of neutrons would equals to 14. You always round it to the nearest integer, so you can either round up or round down depending on what number it is. So it would be 14 minus the number, it's minus the number of protons, and we know the number of protons is right here, minus 7 equals to 7. So in this case, the number of protons, electrons, and neutrons is 7, but remember, it's not always like this. Sometimes you would have more neutrons, for example, or more protons. It could all happen. So let's do another practice. We have iron right here. The atomic number of iron is where? Think about it. Okay, is 26 right here. So that means iron has 26 protons, or 26 positive charge, or a positive 26 charge if we're only looking at the proton. And it has 26 electrons as well, because the number of protons and electrons, the positive and the negative charge, have to be the same in order for iron to be neutral. Now, if we're looking at the number of neutrons for iron, that would equal to this number right here. You want to round it, then you're going to round up. 56 minus 26 equals to 30. So iron has 30 neutrons. As you can see in this case, the proton number, the electron numbers, and the neutron number for iron is not exactly the same, and that's okay. So now you could also be asked a question on what if you have iron with a +3 charge, right? If you have iron with a +3 charge, how many protons and electrons are you supposed to have? So the proton number is still 26. Remember, proton number never changes. Okay? When you look at the periodic table, every single element on here has a number. Every single element on here has an atomic number. This atomic number defines what element it is. So the number of proton makes boron a boron. If you have one more proton, if you have 6 protons, that makes you a carbon. If you have 7 protons, that makes you a nitrogen. So remember, proton number never changes, because if it were to change, then you no longer have the same number, well, you no longer have the same element. So for iron, right here, the number of protons is still 26. So if you think about 26, that's 26 positive charges. So if we want to eventually get to iron +3, you have to have 23 electrons. That means you have 23 negative charges. So if you add it all up, number of protons plus 26, number of electrons is -23. Well, number of electrons, right? If you're asking for a number, then it's 23, but the charge of the 23 electrons would be -23. If you add 26 minus 23, that would be +3, right? So what happened to iron right here? Iron +3 with a +3 charge, what happened to it? It's a regular iron that lost 3 electrons. So I'm going to write that right here. Iron lost 3 electrons. So let's do another example. If we were to have nitrogen with a let's do a -2 charge. So this is nitrogen with a -2 charge. How many protons and how many neutrons do we have? Think about it. So the number of protons is still going to be 7, and then the number of electrons would be 9 in this case, because in order to get to -2, that means you're having 2 extra electrons. So if I were to ask you how many total number of electrons does nitrogen with a -2 charge have, you would say 9. If I were to ask you how many extra electrons does nitrogen have compared to nitrogen -2 compared to nitrogen with no charge, then you would say an extra 2 electrons. So comparing this and this, nitrogen gained 2 electrons. Okay, moving forward, what are isotopes? Isotopes are an element that have the same number of protons but different number of neutrons. So I want you to think about this. What is the difference between element and atom? For example, right here, KCl. There are 2 elements. K is one element. So K is one element. Chlorine is another element. Right? They're two distinct different types of element, but we also have 2 atoms. How about over here? Let's do H2O. This one H2O has 2 different types of element. So an element is what you see on here. It's a bigger category. It's what defines what the atom is. But right here, H2O, we're going to write it out, H2O, we have 2 different elements, the hydrogen element and the oxygen element. But if I were to ask you how many atoms does one H2O have, then you will count There are 2 hydrogen atoms, 1 oxygen atom, so we have 3 atoms in total. If you look at this picture right here, we still have 2 different elements. There's the oxygen element and there's the hydrogen element, but in total we have 9 atoms together. If you count 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 atoms together. So know the difference between element and atom. All right, going back to isotope, what are those? How are all... Okay, here we go. Isotopes is an element. Remember, you're characterizing that specific element. If we're talking about carbon, we're always talking about carbon. It's a specific element that has all the same number of protons. I'm going to underline this and make it bigger. Oh, it didn't work. Never mind. Make it bigger. Same number of protons. Remember, proton number never changes. If we're talking about one element, proton number never changes. But it has different number of neutrons. Okay? So if we look over here, a regular carbon, or we can call it carbon 12, this 12 part is talking about the atomic mass is 12, right? We know the proton number of carbon is always 6. If you look on here, carbon right here has 6 protons. It will always be 6. But if our atomic mass is 12, what is our neutron number? So our neutron number would equal to 6 as well, because 6 plus 6 equals to 12, or 12 minus 6 is 6. But how about if we have a different carbon? It's still a carbon. It's still the same element, but it has a different character. What character does it have? The atomic mass is different. The atomic mass is now 13. So the proton number still has to be 6 because proton number never changes. If it's a carbon, the proton number is 6. But how about neutron? The neutron number will be 13 minus 6, which makes it 7, right? How about carbon 14? When we say carbon 14, what does that mean? It means the atomic mass is 14, which means the proton number is still 6. And then our neutron number would be 8 now, right? Because the neutron number is atomic mass minus proton number. So again, isotope of an element always have the same number of protons but different numbers of neutrons. This is the definition of an isotope, but you should also know how to calculate this. So let's do another example. Let's do nitrogen, for example. Nitrogen 14. So for nitrogen 14, the proton number is, if you look right here, nitrogen is always 7, so proton number is 7. If we know the atomic mass is 14, then the number of neutron would be 7 as well. What if we have nitrogen 15? Then the number of proton equals to 7 still, because it's always 7, it's a nitrogen. And then number of neutron will be now 15 minus 7, which is 8. As you can see, nitrogen 14 and nitrogen 15 are what to each other? They're isotopes to each other, and they have the same number of protons and different numbers of neutrons. Our next one, the types of chemical bonds. First one is, let's do covalent bond first, because that's the strongest bond. Okay, covalent bond is the strongest bond. Covalent bond is a share of electrons between atoms within one molecule. What does it mean when you have one molecule? Let's say we know water is H2O. When you look at one H2O, that's one molecule. If on your desk right now there are 2 H2O times 2, that's 2 molecules. You won't be able to see it because they're so small. If you have, do you get it? H2O is one molecule, right? It's one whole Lego house, for example. But within this Lego house, you have H bonded with O, and then you have O bonded with another H. So there are 3 atoms within this one water molecule. For each water molecule, there are 3 atoms bonded together, and there are these bonds, and we'll talk about the bonds. So let's start with covalent bond. Covalent bond is share of electrons between atoms within one molecule. So for example, right here, each hydrogen has 1 electron on the outermost shell, right? Hydrogen is right here. Remember, if it's in this column, they all have 1 electron on the outermost shell. I'm not going to ask you what a particular atom would have on the outermost shell, well, how many electrons it would have on the outermost shell, but I will tell you, but you have to, use that to answer questions. So for example, right here we have hydrogen with 1 electron on the outermost shell, another hydrogen with another electron on the outermost shell. If you want to form H2, which is also, if you want to write it with the bonds, it's H with another H, there's a bond in the middle. Then I want to ask you, what is the type of bond that connects this hydrogen with this hydrogen? That would be a covalent bond. So how would you know that? A covalent bond is a share of electrons. In order for 2 atoms to share electrons, that means the electronegativity is not very different. Okay, remember, electronegativity is how much one atom, quote unquote, electronegativity equals how much one atom wants an electron. So in this case, for example, when you have 2 hydrogens together, they're exactly the same, right? If they're the same, but they want to form a bond together, there has to be some sort of electron communication going on, but the only type of communication that can go on is a share of electrons, because they both want electrons to the same degree. So every time you see something like O2, N2, F2, where you have 2 or more of the same atom being bonded together, right? O2 is 2 oxygens bonded together, so they both want electrons to the same extent. So the only thing they could do is a share of electrons, okay? But you don't have to have 2 of the same atoms to have a covalent bond, because we have polar covalent and nonpolar covalent. When you have a nonpolar covalent bond, H2, O2, N2, F2, those are examples of nonpolar covalent bond. They're nonpolar because there's no partial charge on either side of the atom at all. There's no partial charge at all because these 2 oxygens all want the electron to the same degree. It's like the 2 dogs that are the same size, same strength, they're pulling the bone together, but this bone is being shared equally, right? However, for a polar covalent bond, such as right here, an oxygen and a hydrogen bond, oxygen is a lot more electronegative than hydrogen. That means oxygen wants the electron a lot more, okay? So then you will have electrons shared unequally, where the electrons, even though it's still, the electrons that are being shared are still between this oxygen and this hydrogen, they're all shifted toward this oxygen a little bit, which makes this oxygen slightly negative or partial negative and makes this hydrogen partially positive, right? If there are electrons that are closer to the oxygen, electrons are negative, that makes the oxygen slightly negative and makes the hydrogen slightly positive. All right, now that you know polar covalent and nonpolar covalent bond, we can talk about ionic bonds right here. So ionic bond is, I'll just not write it. So ionic bond is transfer of electrons between atoms within one molecule. So we're still talking about one molecule. If right here, for example, it's KCl, it's 1 KCl, not 2 KCl, not 3 KCl, is what's happening between 1 K and 1 Cl. The K has 1 electron on the outermost shell. Cl has 7 electrons on the outermost shell. In order for both atoms to be stable and being stable together, this 1 electron will be transferred from the K to the Cl, which means the K has 1 less electron, and the Cl has 1 more electron. And you can take that one step further. What will be the charge of K? Charge of K, if it has 1 less electron, that means now it has 1 more proton than electron, so the charge of K will be +1. And the charge of Cl will be -1. Okay? So as you can see right here, you have K plus. 1 is 1, you don't have to write 1, but I want you to write 1 anyway. For Cl, you have a -1. Okay? So how about, what if we have MgCl2? If you want to write it differently, that would be Cl bonded with an Mg, bonded with another Cl. In this case, Mg transfers 1 electron to each Cl. Okay? So in total, Mg is transferring 2 electrons. 2 electrons get transferred. In total, so each Mg would have a +2 charge. Well, there's only one Mg, but each Cl would have a -1 charge. But if you look at the total charge, Mg is +2, one Cl is -1, the other Cl is still -1. In total is +2, -1, -1, 0. So MgCl as a whole has no charge at all, but if you were to look at the charges for each ion, then Mg is +2 and Cl is -1. So these are the bonds. And then the next one is hydrogen bond. Hydrogen bond is formed between a hydrogen on one molecule and something else that has a negative charge. So in the case of water, for example, because the electronegativity difference between oxygen and hydrogen are so different, oxygen would have a partial negative charge, so you have to know oxygen would have a partial negative charge, and hydrogen would have a partial positive charge. Even though they're still partial charges, unlike these guys that are full charges, you only get a full charge if there's a transfer of electron, if there's an ionic bond being formed. You could get a partial charge if there is a polar covalent bond. So in this case, H2O is a polar covalent bond because of the large difference between this oxygen and this hydrogen. Okay? So now, this is one water molecule, this is another water molecule, this is a third water molecule. Because of the large positive, slightly positive charge, partial positive charge on this hydrogen, and the partial negative charge on this oxygen, there's a bond that could be formed, and we call that a hydrogen bond. This doesn't just happen in water, but all you have to know is that it happens to water and it happens to other molecules that has a hydrogen in there. The last type of bond that we haven't talked about is our van der Waals force. Right here, van der Waals force. So all you have to know is that van der Waals force is the weakest type of bond that we're going to talk about, and that is in between different molecules. Okay, so make sure you know for both ionic bond and for covalent bond, they're both within one molecule, within the one thing that you can hold on to. Hydrogen bond and van der Waals force are both types of attraction between different molecules. So what does within one molecule mean? H2O, this bond right here and this bond right here, those are bonds within one molecule. This is one molecule, H2O. If you have H on its own or O on its own, that's not water anymore. In between, the attraction force in between, an example will be hydrogen bond. Between this water molecule and this water molecule, you have this attraction because of the partial negative on the oxygen and the partial positive on the hydrogen, and you have hydrogen bond. Okay, the next one is being able to calculate the number of the ions based on the charge of the ions. We already talked about that earlier. Know the atomic weight of an element is close to the mass number of most abundant isotopes. So for example, carbon, if you look at the periodic table, the weight is 12.01. You now know that there's carbon-12 isotope, one type of isotope of carbon. There's carbon-13, there's carbon-14. Which one is the most abundant, meaning which one do you have the most amount of? That will be carbon-12 because carbon-12 is most similar to the atomic mass number that you see on the periodic table. Next one is polarity. We're going to talk about this. You have a polar versus nonpolar molecule. So this will be a nonpolar molecule where all the electrons are being shared equally within the cell or within the bond. And then you don't have a pole, you don't have a partial positive or negative charge at any part of the molecule. However, if you have an OH bond, for example, or H2O, then you have a negative end and a positive end. That makes you a polar molecule. We talk about electronegativity, and electronegativity is how much something wants electrons. All right, now we're moving fast. Properties of water. Basically, the most important thing is, as we talk about in class, water is polar. So this is one water molecule, right? Because when we're talking about polar versus nonpolar, we're only talking about one molecule. This is a common misconception that some students have. When we talk about polar and nonpolar, it's one molecule. Water can form hydrogen bond. So you wouldn't say water is hydrogen bond because one water, this is one water. You can't have a hydrogen bond within one water. You have to have multiple water molecules interacting with each other, attracting to each other in order to have hydrogen bonds being formed. So hydrogen bond is formed between different water molecules. This is why it's so important to talk about what does it mean to have one molecule, right? Oh, good point. On to, as we're talking about molecule, there's a difference between a molecule and versus a compound. So if you were to draw a circle of every type of chemical equation that you see, CH4, so let's do CO2, O2, F2, all of these are molecules. Okay, everything is a molecule. However, not everything is a compound. In order to make something a compound, you have to have more than 2 elements. So does this have more than 2 elements? This is why you have to know the difference between an atom and an element. This is one type of element because this is only one box on the periodic table. This is another, as this molecule on its own, it's only one type of element. So these two, O2 and F2, they're only molecules and they're not compounds. In order to have a compound, it has to be composed of more than 2 elements. So CH4, for example, that is a molecule because everything is a molecule, but it's also a compound. So CH4 is a molecule and a compound. CO2 as well because we have 2 different elements, even though we have 3 atoms. It's both a molecule and a compound. All right, now water is polar. We already talked about this. Water is polar because has a positive charge and a negative charge. You have to know oxygen is what has the negative charge, and hydrogen is what has the positive charge. Solvent. So universal solvent. So water can dissolve polar molecules and ionic molecules. We call this like dissolve like. So what that means is that because water is polar, right? If you look right here, water dissolve salt. Right here, for example. So when water is dissolving salt, salt is NaCl. You have a bunch of NaCl in a salt block. In order to dissolve the salt, the Na and the Cl has to be pulled apart. They form an ionic bond, which means when they're pulled apart, the Na donates an electron to Cl, which makes Na have a +1 charge, and Cl will have a -1 charge. In order for Na and Cl to be pulled apart, water is able to do this. So water would have the negative charge, negatively charged oxygen, or partially negative charged oxygen facing toward the positive charged Na and pull it apart. And the positively charged hydrogen will be facing toward the negatively charged chlorine and pull those away as well. Let's look at a different picture of it right here. We have something that's ionic would have a full positive or multiple full positive charges and a negative charge on the other atom, and then water can pull those away, pull those apart by surrounding the atom that you're trying to pull away. Okay, so another one right here, for example, right here you have all the hydrogen facing the negative charge. So that's what makes water a good solvent. So water, oh right, we already said this. So water is a good solvent because it is what? It is hydrogen bond, or it is polar? Which one? It is polar because you can only talk about one water molecule using the word polar, meaning water has the partial positive and the partial negative. So water can dissolve polar molecules because the polar molecule also has the positive and the negative, which allows water to surround those molecules. And then it can also dissolve ionic molecules that has a full positive or negative charge. Cohesion is water stick to water. Right here, the hydrogen bonds being formed between one water molecule and another water molecule makes cohesion happen. So water stick to water is cohesion. Adhesion is water stick to other things. So when you put a droplet of water on your table, the water molecules are sticking to the table, or if you have water molecules on your wall, right? Sometimes it sticks on there for a little while. That happens because of adhesion. Surface tension is easier if you were to look up a picture. So here's surface tension. Look at this one. So when a bug is trying to walk on water, there are all these water molecules forming bonds between each other, between different water molecules, not within one water molecule. Make sure you know the difference. These hydrogen bonds that are formed between the water molecules, or the cohesion that's happening between the water molecules, allow the bug to walk on water because it's not breaking the bonds yet. If you look right here, for example, if all these are water molecules, they all form bonds, hydrogen bonds between each other, and that's surface tension. Capillary action. So here's capillary action. Right here, for example, so if you were to put a very thin tube into water, the water will get sucked up by the tube without you having to do anything, because water can stick to each other, which is cohesion, and water can stick to the side of the capillary tube, which is adhesion. So capillary action is a result of cohesion and adhesion. So the example that I gave you was for a plant, for example, water can travel from the root all the way to the leaves because water can drag each other up through cohesion, and water can stick to the side of the capillary tubes inside the plant and pull themselves up, as well as water is evaporating through the leaves. Water in liquid form is less dense than solid. Water, liquid versus solid. So if you look at the structure of water molecules that are in liquid water, you don't have to form those very condensed solid structure, so it's more dense than a solid water, which is ice. When ice is being formed, all those hydrogen bonds of water have to be arranged in this way, in order for the ice to be ice, and that's what makes ice less dense. So this is also caused by a hydrogen bond. High specific heat takes a lot of energy to heat up or cool water. And when water is cooled down, a lot of energy is released. So in order for a molecule, in order for a liquid to be heated up, those molecules have to move faster. In order to move faster, you have to break the hydrogen bond. Okay, so in order to heat up, then molecules have to move faster. In order to move faster for water, we have to break hydrogen bonds. Breaking hydrogen bonds take a lot of energy. So an example of water having high specific heat, you can't just say specific heat because everything has a specific heat, but water has a high specific heat. An example of that would be in the summer, when you go to a pool, the pool heats up much slower than the atmosphere. It could be very hot outside and the pool is still not very hot because it takes a lot of energy to heat up water to break all those hydrogen bonds. Two types of mixture, finally. We're on to what we talk about on Friday. So if you already know those really well, you don't have to continue on with the video, but obviously reviewing with me is always good. What's the other one? Solution versus suspension. If you were to look at a picture right here, on the right side is your solution, and on the left side is your suspension. So whether it's a solution or a suspension, they're both mixtures, but they're both, you have to have two or more components or types of molecules mixed together, right? So there are many differences between a solution and a suspension. Just by looking at it, you can see that a solution is the physical character of all parts of a solution is all the same, but for a suspension, it's not all the same, right? For a solution, you can't separate the solute and the solvent very easily. But for a suspension, such as salt water would be a solution. If you have dirt water, if you just leave it there long enough, the dirt and the water will separate. What makes something a solution? A solution has to be made if water can dissolve whatever is dissolved into water, or if you have other substances, they can dissolve each other. Remember, like dissolve like, right? So something polar, such as water, so if you have something polar, can dissolve polar or ionic. So in the case of water, water is polar, it can dissolve polar molecules and ionic molecules. Nonpolar can dissolve nonpolar. So there are vitamins that are nonpolar. Those can only be dissolved in fat and not be dissolved in water in your body. Know the difference between a solute and solvent and be able to identify what's a solute and what's a solvent. Example, let's do sugar water, I guess. Sugar water, sugar being dissolved. So that's a solute. And the water is the molecules that are dissolving sugar, so those are the solvent. If you can't tell which one is whichever one you have less of, sugar in this case will be the solute, water will be the solvent. Another example, if you're dissolving carbon dioxide into water to make soda water, if you dissolve carbon dioxide into water to make soda water, then the carbon dioxide is your solute and the water is your, did I say? If you're mixing carbon dioxide and water, carbon dioxide will be your solute because we have less of that, and water will be your solvent. Organic and inorganic molecule. Organic has a carbon somewhere in the molecule, such as CH4, CO2, I guess. Well, organic molecule also has to have a CH of some sort, so CO2 is not organic. C4H12O O6, for example, is a more complicated one. It's also an organic molecule. Inorganic doesn't have a carbon, so H2O, for example, is an inorganic molecule. Hydrophobic and hydrophilic. Hydrophobic is scared of water. So this, we didn't go over this in class, so this won't be on the test. Scared of water, so for example, if something is nonpolar, they're hydrophobic because they can't be mixed up with water. Hydrophilic is want to be around water. So for example, a polar molecule or ionic, those can be mixed up with water, so we call those hydrophilic. So phobic is something you're scared of, right? So that's scared of water. Now, last one. Hooray! pH. pH scale. So pH scale is a measure of, let's do this one. So the pH scale is a measure of hydrogen concentration. Okay. However, how it works is kind of backwards. So 0 to 7 actually have more hydrogen concentration, but over here you have less hydrogen concentration. The more hydrogen that you have, right, towards this end, the 0 end has the most amount of hydrogen concentration, and the 14 has the least amount of hydrogen concentration. The more hydrogen that you have, the more acidic you are, and the less hydrogen you have, the more basic or acid, or we call it base toward this end. But I could also ask you, and in the middle is 7. 7 is neutral. H2O is neutral. Okay? If I were to ask you, comparing comparing pH 0 to pH 4, which one is more acidic? pH 0 is going to be more acidic because it's, on this end you have more hydrogen, and it will be more acidic. So very, very acidic, middle-ish acidic, very weak acid. You have neutral, weak base, middle base, there's no such word, and then there's strong base. Okay, so let me write that down. So toward this end you have strong acid, and then toward the middle you have weak acid because you have slightly less hydrogen than this end, and then immediately you would have weak base, and then you have a strong base. So don't memorize these, try to understand what's going on in here. All right, I think you're very prepared for Monday. Good luck.